Welcome to my video course on RAMS engineering for railway systems. Today we're going to explore the pretty fascinating history of RAMS management. We'll uncover how it evolved from early aviation to become the absolute backbone of modern railway operations worldwide. We're going to dig deep into why the highly complex, interconnected transit systems that, let's be honest, we all take for granted, simply couldn't exist today without this vital framework working behind the scenes.
Okay, let's take a quick look at the agenda. We've got 5 main parts: the aerospace origins, the rise of systems engineering, entering the railway industry, the European standardization, and finally, global adoption and beyond. So let's dive right in and trace how this critical engineering discipline evolved over the decades.
Section 1. The aerospace origins. We begin our journey by looking to the skies, decades before modern high-speed trains were ever even conceptualized.
But before we explore its history, let's establish exactly what it is we're studying. RAMS is the essential framework ensuring that when you need a complex system to work, it operates predictably and safely. It literally stands for reliability, availability, maintainability, and safety. It's this intricate engineering discipline that integrates these 4 key characteristics directly into a system's core design. Reliability dictates how long a system operates without failure. Availability ensures the system is actually ready to go when you need it. Maintainability measures how quickly and easily you can fix it. And safety, well, that ensures that even when things do fail, they fail without causing harm. The ultimate goal, to successfully achieve defined traffic services safely and cost-effectively. Honestly, without RAMS, the high-speed rail networks we rely on today would be mathematically impossible to run safely.
So the foundational practices of RAMS actually originated way back in the 1930s aerospace industry. It started as a way to systematically evaluate the safety of early aircraft. Aviation engineers urgently needed a rigorous method to assess mechanical failures and human errors. Because, unlike a broken-down car, an aircraft experiencing failure literally falls out of the sky. By the 1940s, the very first structured technique for reliability and safety assessment was developed. It was called failure mode and effect analysis, or FMEA. By the 1950s, this had transformed into a major, standalone engineering discipline for aerospace. And just to show how these frameworks constantly evolved to handle more complexity, by the 1960s, Boeing took that FMEA technique and updated it into FMCA. They basically injected criticality analysis into the equation, which allowed engineers to mathematically prioritize the most catastrophic risks first, a real game changer.
All right, moving on to Section 2, Rise of Systems Engineering. Let's see how this builds into the broader world of industrial engineering as technology rapidly advanced.
By the 1980s, RAMS management was widely adopted alongside the massive rise of systems engineering. The goal was to strictly control potential threats across all sorts of mission-critical industries. What emerged from this is what we like to call the trinity of impact: safety, availability, and reliability. They share this profound cause-and-effect relationship. Safety reduces those risky, unplanned interventions. Availability serves as the foundational guarantee that the service can actually run in the first place. And reliability? That pushes continuous punctuality, which directly preserves revenue. You just can't separate them if you want a complex system to function and actually survive in the real world. It's a constant, delicate balancing act.
So the crucial point here is that industries finally realized they couldn't just react to failures anymore. They had to actively engineer risk out of the system from day one. Implementing RAMS management meant effectively defining, identifying, assessing, and controlling all potential hazards right from the earliest concept phase. We're talking way before a single piece of metal was cut or a line of code was written. If left unchecked, these inherent risks could lead to loss of personnel, massive environmental degradation, and severe property damage. But more importantly for the survival of the business itself, it meant proactively protecting the bottom line from catastrophic impacts on revenue.
Section 3. Entering the railway industry. This brings us to the crucial moment when these rigorous aerospace and systems engineering principles finally made their way down to earth and onto the railway tracks.
There's a really interesting geographical shift here. The U.S. railway sector actually spearheaded the adoption of RAMS in the early 1980s. They were the very first to truly integrate it into their systems engineering processes. European railways, on the other hand, well, they fully embraced the discipline about a decade later in the early 1990s. Now, you might be wondering why the delay and then the sudden leap in Europe. It was mostly driven by massive alterations in contracting schemes. Historically, European railways were state-owned monoliths that basically designed and built their own systems. But as they started separating infrastructure from operations and buying complex systems from private, external suppliers, they couldn't rely on internal handshakes anymore.
They required strict, formalized, mathematically rigorous engineering contracts to guarantee safety and performance, and RAMS became that essential shared language. But why exactly did railways suddenly need this framework so desperately? Well, they were facing a massive paradox. On one hand, their technical performance, things like high-speed running, long-distance driving capabilities, and high-capacity transport, was drastically improving. But on the flip side, their operational issues were severely hurting their competitiveness against other transport sectors like commercial trucking and aviation. I mean, faster trains just meant bigger bottlenecks if a single component broke down. They were bleeding efficiency due to frequent cascading service delays, skyrocketing total ownership and maintenance costs, and of course, the looming threat of catastrophic damage for humans and environments caused by high-speed rail accidents. The technology had simply outgrown their traditional maintenance strategies.
Let's turn to Section 4, the European Standardization. We'll look at how these regional, kind of disjointed practices were eventually unified into a strict, continent-wide doctrine that completely changed the industry forever.
The pivotal milestone arrived when CENELEC stepped in. Now, CENELEC stands for the European Committee for Electrotechnical Standardization. Before they intervened, the European railway landscape was, frankly, heavily fragmented. Cross-border travel was an absolute engineering nightmare because France, Germany, and Italy all had different safety math, different signaling requirements, and completely different risk tolerances. CENELEC recognized that as these rail networks became deeply interconnected, the standard for safety and reliability absolutely had to be uniform across the entire continent. To solve this mess, CENELEC officially standardized railway RAMS for the very first time in 1999. They did this with the publication of the landmark EN 5126 standard. And this wasn't just some helpful set of guidelines. No, this was an absolute game changer and a strict mandate. It provided railway duty holders and private suppliers throughout the entire European Union with a single unified process. Basically, if you wanted to sell a train or build a signaling system in Europe, you now had to mathematically prove your RAMS case using this exact standard. It guaranteed a consistent approach to safety across every single project. What's genuinely fascinating about the EN 5126 standard is how it maps RAMS into what's known as a V-shaped life cycle. It fundamentally shifted the industry mindset from reactive troubleshooting to proactive engineering. It guarantees that availability and safety are engineered at every single stage. You conceptually start with high-level design and definition, breaking the system down. Then, you move down into the manufacturing and implementation phase. After that, you climb back up for rigorous testing, validation, field monitoring, and daily operations, putting it all back together. This V-model proves that RAMS isn't an afterthought or a final inspection. It's baked right into the very DNA of the project, from conception all the way to eventual decommissioning. Which brings us to our final section, Section 5, Global Adoption and Beyond. Let's look at how a highly successful European standard managed to conquer the globe and become the undisputed blueprint for modern railway safety everywhere. The crucial takeaway here is that the sheer brilliance and effectiveness of EN 516020 just couldn't stay local. The mathematical rigor was simply undeniable. So just 3 years later, in 2002, the international engineering community effectively copy-pasted it, adopting it on a global scale as ISC 622078. This exported the European RAMS model to the rest of the world, from Asia to the Americas, permanently standardizing global rail operations and providing a massive leap forward in international operational excellence. This parent standard eventually birthed an entire family of highly precise regulations that continue to govern global railway projects today. You have IEC 62278 for overall international RAMS, but as digital signaling and automated train control began taking over, engineers realized traditional physical standards just weren't enough. I mean, software doesn't wear out like a brake pad, right? It has hidden logic bugs. So EN 5108 was developed specifically to manage the unique risks of complex software. Meanwhile, EN 5129 was created to lock down safety-related electronic hardware against random physical failures. Together, these specific standards force continuous modernization. They make sure that high-density digital networks can handle massive stress while ensuring that millions of passengers commute safely every single day without a second thought.
And that brings us to the bleeding edge of today. With trains getting exponentially faster and digital signaling systems becoming infinitely more complex, how will RAMS evolve to protect the next generation of commuters? Moving forward, this framework is going to have to continually adapt to handle artificial intelligence, autonomous networks, and severe cybersecurity threats. Because let's face it, a hacked train is just as dangerous as a broken one. It's a critical engineering challenge that's constantly unfolding. Thanks, we can see you next day.